Good morning, and good morning to all of you. And for some of us, it's a good evening. And in Beijing, it is around evening, and Singapore, it's afternoon, I think. So indeed, it is a great pleasure to moderate this second pre-conference webinar series today. We had a very successful webinar, first webinar yesterday. At the very outset, I thank the organizers of this conference on environmental monitoring and management for giving this opportunity for me to moderate this webinar on a very important topic, advances in wastewater management. So I welcome all of you. There are 117 participants here. We welcome all of you. And a special welcome to our two eminent resource persons, scientists, eminent personalities, Professor Ning and Professor Wei. Professor Ning, Wun Jern, and Professor Yuansong Wei. So we are very happy and we are very fortunate to have these two resource persons today in this webinar series. I will formally introduce them later on. So I welcome once again all of you. There are a couple of instructions for all participants. We humbly request all participants to mute microphones and also turn off video. It doesn't mean that you can communicate, you can us. You can communicate with us in a chat section, in a chat box, not question and answer section. In a chat section, you can type your questions relevant to the topic that we are going to discuss today, and make sure that you post it to all panelists or all attendees so that others also knowing there is a question for the panelists. So we will take all the questions possibly in the end of this webinar series, and we will try to discuss it with the resource persons. So only questions related to the seminar you can type on the chat box. If you have any problem with the audio, video, please settle from your machine. And if you have further questions, if time is restricted, we can communicate with you over the email. And we are recording the webinar, and we can share that recording with you later on. So we had a fourth webinar series in this pre-conference of environmental monitoring and management. We had one yesterday, as I said earlier, and we are having the second one today. And third one, it is on environmental impact assessment. That is on next week, 15th October. And the fourth one on water quality monitoring, that is on the 16th October. And we hope all the participants will enjoy, will participate in this webinar. So today title is Advances in Wastewater Treatment, and we have a Professor Wun Jern from Nanyang Technological University, NTU, Singapore, and also Professor Yuansong Wei from Chinese Academy of Science, China. So our session will follow this program. First, I am just doing this introductory and welcome note. And second, we will invite Professor Nung to take the floor on his title. And then after 20 minutes, and then we will move to the Professor Wei. He will take the session for another 20 minutes. And we will end up this session. We will have a 20 minutes for panel discussion. If you need some more time, still we can go. So then we are supposed to finish by 3:50. So if I want to introduce Professor Ning, it's a very difficult task for me to introduce him. Basically, we have worked with him for a long time, and he is a frequent visitor to Sri Lanka, and he has involved in many projects in Sri Lanka with us. So he is a professor, president chair in civil and environmental engineering. Presently, he is a principal lead of EBiG hopefully he will introduce this EBiG in his presentation. That is the Environmental Bio-Innovations Group. Very interesting group. Now he is attached to the School of Civil and Environmental Engineering in TU, Singapore. So he had a lot of work. He pilot scale, laboratory work, pilot scale, in the large commercial scale. He has done a lot of work on this wastewater treatment. I think his citation is more than 10,000, I think. So he has supervised many postgraduate students. So today he is going to talk on the issues and responses in wastewater treatment. Today, going to tomorrow. I hope you will get a lot of insight of this whole story of the wastewater treatment in a concept wise, in a practical wise. So that you will get a lot of research ideas, research topics from his presentation, I think. And also you will get a solution for your problem in the wastewater management. So I am very pleased to invite Professor Ning to take the floor and continue your presentation.
Thank you, Professor Mowjood. I should thank Professor Mowjood, colleagues and friends in Sri Lanka. For those of you who have worked with me and know me well, you would know that I am very fond of Sri Lanka. It reminds me a lot of my old home. So I had really looked forward to coming to Sri Lanka this time, but unfortunately, COVID-19 has really messed up the plans. Nonetheless, let me share with you some of my thoughts on wastewater treatment issues and responses. Now, please do note, as Professor Mowjood had pointed out a few moments ago, my presentation will not be entirely on research. It will not be entirely on applications, but on a mix of R&D and applications. The reason for this is because EBiG, this is my own personal research team, EBiG has a rather unusual way of working. We typically would start a research project and we would not end until we take the project's outcomes out into the field. So this means that we travel with our outcomes all the way from laboratory to full-scale application. So later on, when I show you pictures, please do note that these are pictures of real full-scale facilities that have been implemented, either designed or even built by the group that I lead. So let me now take you to this particular presentation, wastewater treatment issues and responses. And I'm talking about what's happening today and what can probably happen going on to tomorrow. Can I have the next slide, please? Thank you. Now, obviously, wastewater treatment is not totally simple. There has been many issues concerning wastewater treatment. And if I were to identify one particular issue that recurs frequently, this would be failure to meet discharge limits. Now, this is particularly so when we are dealing with biological treatment plants. As those of you who have dealt with living organisms, you realize that these organisms do not always play according to our rule book or do what we would want them to do. So there are times when they get upset, and as a result of that, the performance of the process would not then be able to meet with the discharge limits. So the cause of this is process instability and failure. Now, if you're looking at environments where enforcement of discharge limits is very strict, then obviously this is the major issue operators of wastewater treatment plants will face. So, you know, in the Singapore context, you could have the managing director of the company going to jail. So it is as serious as that. Can I have the next slide? Right, so let's explore a little bit what causes process instability and failure? There are numerous reasons why the process can become unstable and eventually possibly even failing. Now, I start with something that happens very frequently, and this is loading. Now, for those of you who are not so familiar with wastewater treatment plant operation, you did be surprised that wastewater treatment plants are not only overloaded, but they can also very often be underloaded. And both overloading and underloading in terms of organic loads, in terms of nitrogen, for example, in terms of hydraulic loads, this can cause process instability. Now, composition is the next big thing. This could be changes in the composition. In fact, just before joining this webinar, I've been exchanging messages with my engineer on site. One of our plants is going through a difficult period at this moment because the factory that is discharging the wastewater has changed its product line. So it does campaign manufacturing, and right now the composition of the wastewater has changed. And the wastewater treatment plant, the biological process, is experiencing difficulties. Now, the next bit about composition is the issue of persistence and recalcitrance. This means that even if your biological process is stable and performing, you could still fail to meet the discharge limits because there are certain compounds in there that resist biological degradation. And as a result of that, they pass through the treatment plant untouched. Now, I highlight in red the last point, and this is inhibition. In the extreme case where you experience toxicity in the process, then of course you lose the whole process. The plant fails completely. Now, much of this can be addressed with the selection of the type of reactor that we use. Can I have the next slide? Next slide, please. Thank you. Now, I show on this slide a series of full-scale reactors that are associated with my group. By the way, all of these reactors are SBRs, so they are sequencing batch reactors, with the exception of the last one, that is a membrane sequencing batch reactor. So it's a little bit different from the top two. But the key point that I would ask you to take a note of is right at the beginning of this particular slide, and you see three reactor configurations. This would be the CSTR, the plug flow, and the cyclic. Now, for those of you who are terribly theoretical, you want to get the theory correct, then you would argue that actually the cyclic and the plug flow are similar, except the plug flow operates on a spatial frame, whereas the cyclic operates on a temporal frame, but the effect is the same. Now, the next bit, the next bit shows you the impact of running these different types of reactors. So CSTR would give you good dilution internally, whereas the plug flow types, whether they are temporal or spatial, would give you the concentration gradient, and this drives the kinetics that you want. In other words, you get better performance out of the reactor. But having said this, choosing the wrong reactor will make it very difficult for the operator to run the treatment plant. So for example, if you are going to receive a wastewater with inhibitory compounds, putting in a plug flow reactor may not be such a good idea. Next slide, please. Right, so how do we enhance process resilience? Now, by process resilience, I mean to say, how tough can you make your process? In other words, how resistant is your process to upsets, to failures, and so on. Now, one of the key ways that we have to do this is to increase the microbial population. And this means that we are going to go into biomass retention. Now, I've listed three ways that we typically practice when we try to go for biomass retention. And this would be running a sludge blanket, doing biofilms on fixed beds, on expanded beds, on moving beds. And of course, we would do membrane separation. Membrane separation provides an absolute barrier So you keep theoretically all of the biomass that you can have inside of the reactor. Now, if you now want to take this one step further, meaning you want to go beyond just increasing the population, then the next level would be population selection. And this is where the issue of proper acclimation and then collecting samples and performing molecular biology to profile the population, to select the appropriate players that you would want to accumulate. And then you want to culture this, and you want to harvest this, and you want to store this after freeze drying in a cold store. Now, in fact, we do this at full scale. We do this particularly when we are addressing chemical wastewater, where failures can occur very frequently, and it's very hard to get the correct population done up within a short period of time. Next slide, please. Right, this slide here, starting from the top, going down to the bottom, shows you different reactor configurations that would then allow us to accumulate the biomass. All right. So right at the top, you have a sludge digester that using the hydraulics and hydrodynamics inside of the vessel, we accumulate a thick layer of sludge at the bottom. Then you have the filters. This would give you the biofilm. So this would be picture number 3 from top to bottom. Number 2 is a sludge blanket. And the last one, the fourth one, is the hybrid reactor. This combines a biofilm with a sludge blanket. Now, for those of you who are wondering what kind of wastewaters we have designed these reactors for, the top one is for palm oil mills, meaning vegetable oils. The second one is for pig farms. The third one is for food industry. And the last one, that one is very topical at this moment because of COVID-19. This one was designed and built for a rubber gloves factory. Next slide, please. Right. Supposing now you have already built up your population and you still want to push the process further. So this is where process performance enhancement comes in. Now, really, if you look into the operation of a biological process, much of it is driven by enzymes. And of course, when we go into the selection of certain microbes, we are in effect selecting enzymes because microbes, the selected microbes will then release the target enzymes. Now, if you feel that your reactors are not producing enough enzymes for whatever reason, maybe the population is not sufficiently large yet, then we could be supplementing enzymes. Now, a very common application would be for hydrolysis. So supposing you're doing anaerobic degradation and you have things like cellulose coming in, then we may add in cellulase. So this is to hydrolyze the feed material more quickly to release the sugars so that then we can go on to the next stage of the biological process. But there are also instances where we select very specific enzymes to target very specific compounds. Now, I provide you an example of this when you start to look at the green lines further down the slide. And this refers to signaling compounds. My own research group has spent a great deal of time working with signaling compounds. Believe it or not, microbes do communicate with each other. In fact, if they cannot communicate with each other, then it would be very difficult to form flocks and biofilms. So one of the things that we do if we want to form biofilms and flocks quickly is to inject a signaling compound into the system. And the microbes then are signaled to come together and they form a flock or biofilm, or sometimes we actually send a signal to break up the biofilms. In the extreme, we could send a signal in to try to slow down the growth of the population, because this then relates to excess sludge. So if we can slow down population growth, we are slowing down sludge yield. Next slide, please. This shows an example of one of the compounds that we have been developing, and this specifically targets fungi. Now, if you are operating wastewater treatment plants, or you're into agriculture, by the way, the same thing applies in agriculture. Fungi may not always be a good thing unless you happen to be very interested in breaking down cellulose or hemicellulose. So oftentimes we want to control the growth of fungi. Now, this particular compound, I'm not giving you the name because there's an IP connected with it. This particular compound that we have developed targets the fungi and it blocks the fungi from multiplying. Can I have the next slide, please? Next slide, please. Right. Now, if you have done all of that, then the next step would be, how do I make sure that the system continues to perform the way that it has now been set up to do? So this is what I call enhancing process integrity, meaning that I don't want the process to do anything else other than what I have planned for it to do. Now, here's where research work and applications of sensors comes in. Now, for those of you who are working in the lab with your reactors, you would have come across pH sensors, DO sensors, and for those who are running full-scale plants, you would have flow sensors and all that. I call these conventional sensors. Very important because minimally this is the base level that we will start off with when we put in a sensor system. But going forward, we now want to look deeper into the biological process. And offhand, I can think of two sensors that we are now using to track the behavior of the population. One is SOUR. This is offline. We are tracking the metabolic behavior of a microbial population by looking at the oxygen demand. And from that, we can interpret whether there is an issue with degradability, there's an issue with inhibition, and take the appropriate countermeasures. But what is even more interesting now is an electrochemical biological online sensor that we are beginning to install. And this tracks electrical signals. Now, when microbes degrade things, they actually release electrical signals. And we are picking up these signals and making an interpretation of these signals. So when the signals change in a particular way, we can then say, right, no good. There is possibly something inhibitory entering the system, and we would now need to take countermeasures. Next slide, please. And once we have the sensor system in place, the next level of work would be to couple this sensor system with an AI system. Now, the whole idea is when we put in artificial intelligence with our process control algorithms, we are leaning on the AI system now to help us make decisions. Now, by the way, we do not allow AI systems to decide for us. The AI system proposes possible decisions for us to adopt. Now, once we have those, then the next level would be to incorporate the AI system, interface it with mechanical elements. Say, for example, pumps, valves, blowers, chemical dosing systems, and so on. Now, the idea is, and maybe perhaps this is peculiar to Singapore, the idea is, of course, we reduced our requirement for manpower. So we are putting most of the operator responsibilities to the AI. And with the AI, then we also go on to save energy because it's not going to allow you to dose more than enough dissolved oxygen. And with all these controls and oversight, you do end up with a more stable process. Next slide, please. So what is next? So I'm coming close to the end of my presentation now. So assuming now you have this process, you have this treatment plant that is working very nicely, what would be the next lot of questions that you would begin to be addressing? One of the common ones would be excess sludge. This would require either incineration. The days of disposal in a landfill are coming to an end now, at least in our context. We cannot just put sludge into a landfill, so we would either incinerate or pyrolyze. And if we pyrolyze, we end up with char, and that represents a store of a fuel, or it can be applied to the land as an agri supplement. Now, if in the event that, for example, you have a COD that cannot meet discharge limits, and if you know that your biological process has done all that it can possibly do, then this is where physical chemical processes will be added in. Now, there are two possible processes. One is hydrothermal oxidation, where we are looking at wastewaters that contain substantial amounts of particulates. And the other one is supercritical oxidation, where your wastewater does not contain substantial amounts of solids. Now, beyond all this, a recurring issue now because of ESG and SDG and so on is the question on sustainability. We have to, even when we are treating wastewater, now we have to be sensitive to the issue of energy. We have to be sensitive to the issue of chemical use and the residues that result as a result of this use, and also the possibility of resource recovery. Now, I would like to take you through quickly the next few slides that show pictures of some of this. Next, please. Yes. Now, I understand my colleague, Professor Wei, is going to talk about peak waste. What I show you is a picture of one of the full-scale systems that we implemented. This is for a farm that has 400,000 pigs. So this is a farm that operates pigs growing, slaughterhouse, and meat packing house. So why is this important from the sustainability angle? This plant, if you look at the green mushroom things at the back, allows energy recovery. So we are recovering biogas from the wastewater that is coming out. Next slide. Can I have the next slide, please? Right. Now, this is wastewater for a bean curd factory. In our language, we call it tofu factory. And here we are recovering energy, and we have a system that results in low sludge yield so that we don't have to be overly bothered with excess sludge disposal. Again, the sustainability angle is number one, energy recovery, and number two, we have less chemical use further downstream because we are producing less excess sludge. And my final slide, please. And here, this is a recently installed facility, and it is using a new design from the group. We call that the EBiG. This is the anaerobic pulse bed filter. We use a pulse bed because of suspended material, and if you use a fixed bed filter, there is risk of clogging. Now, this particular facility has been designed to take in strong wastewater, but yet the biological process will treat the wastewater to a level that will allow water reclamation. And the water reclaimed is channeled back into the factory. Now, for those of you familiar with industrial applications, you will notice how rigid the requirements are for this, because this is for a food manufacturing facility. So the water that is recovered and sent back into the factory obviously has to achieve a very high standard, very high quality, and beyond that, very consistent in terms of the quality. So these reactors here are both anaerobic, that's the EBiG, and aerobic, that is the SMBR. And with that, then, I would like to thank you for your attention. I look forward to your questions later on. Thank you.
Yeah, thank you very much, Professor Ning. It was very enlightening talk, and I hope you are living with the microbes and you can talk to the microbes. Okay, so the next one is we will move to the next presentations, and then if you have any questions, you can type in a chat box and send to us. We will get all these questions at the end. So I'm going to introduce my next resource person. So next our resource person is Professor Yuansong Wei. So he's a professor, director of Laboratory of Water Pollution Control Technology, Research Center for Environmental Sciences, Chinese Academy of Science, China. So he has done a lot of work on this wastewater treatment from laboratory scale to commercial level. He's a very frequent visitor to Sri Lanka. So he works on this anaerobic treatment process, and he would like to share his new innovative techniques in wastewater treatment. So he would like to talk on the shortcut process of combining magnetic coagulation and sequence membrane reactor for treating high strength wastewater. Now, Professor Wei, it is now over to you. Okay, so we'll wait until Professor Wei is connected. So let's take one or two questions to Professor Ning until he comes. Professor Ning, is it all right for you?
Sure.
Yeah. So we have 200 participants. So we got some questions, a couple of questions. One question is because you nicely put that the problem as instability in the processes, and then you told that the inhibition is the big issue. So you have come out with these four things that as a solution: enhancement of resilience, performance, integrity, and system operations. So it is nicely we have taken it. So the participant asked, can we enhance the process resilience by coupling biological system with physico-chemical processes?
Right. Actually, that is what we would typically do. So the biological process often can be preceded by physico-chemical processes. And I would say that one of the more common types of processes would be oxidation and also sorption. All right. So we would use this to degrade or to remove certain potentially inhibitory compounds before the rest of the wastewater gets into the biological process.
Yeah, so the next one, thank you. The next one also related to this one, how the inhibition can occur and how to identify the issues related to inhibition. So how we get it, there is an inhibition in the process.
Right. Now, in domestic sewage, inhibition is not very common unless somebody has illegally discharged something into the sewers. But when you are operating a facility for a factory, for example, let's say something very innocent, which would potentially look very innocent, like a food factory, you might wonder, why would there be something inhibitory or toxic coming out of a food factory? Because after all, we eat the material that's coming out. You did be surprised that actually food factories are notorious for discharging wastewaters that are inhibitory. Now, the reason for this is food factories have to clean their production lines very, very carefully. Otherwise, their products are compromised. And guess what? How do they clean their production lines? They use a lot of disinfectants. And if the disinfectants are any good, obviously the disinfectants are not only inhibitory, they're outright toxic. So if the disinfectants then go out with the wastewater and goes to your treatment plant, you're obviously going to have lots of problems. So that's just one example of how inhibitory or toxic materials can get into a wastewater from a seemingly innocent industry, all right? Now, how would you know that there is inhibitory compounds coming through? Unless you do specific tests, you wouldn't know. So that is why we now, if you recall on one of my slides, I talked about the SOUR sensor. I talked about the electrochemical biological sensor. Now, we use those sensors to pick up potential signs of potential inhibition. If you don't have those, then it's going to be pretty difficult.
Yeah, that's quite interesting of this, the inhibitors, the toxic materials are coming from the system itself, the process itself, without our knowing. Unintentionally, we are adding this toxic as a raw material, but although we are not considering it as a problematic thing. Yeah, Professor Ning, I have one question that it's a very dynamic system that we are handling. And then you said that resilient performance, integrity, and system operation will solve our inhibition problem, and we can bring the process in a stable state. So do you think that stability is it itself is a dynamic, or it's again and again we have to be very careful on this stability? How do you feel it?
I'm sorry, Professor Mowjood. I have to. I'm sorry, I have to say this to you. Biological processes are always dynamic.
Dynamic.
So, in fact, I always like to say this to my colleagues. One of the biggest lies that professors tell their students is there is steady state. There's no such thing as steady state. In my mind, there's no such thing as steady state. And if we design on the basis of steady state, you're going to get into a lot of trouble. There's only transient state. Now, what does that mean? It means that things are always changing. So your population of microbes in terms of numbers and types are constantly changing. The idea, of course, is when we do all those things with sensors and control this and that parameter, the idea of all that is to ensure that whatever changes take place, these changes are occurring within a bandwidth that we can live with, right? And once you get out of that bandwidth, then you have process instability. So when we design a plant, the plant is always designed to operate within a certain bandwidth. So that is why, by the way, that is why certain types of reactors are more robust when it comes to creating this bandwidth. So for example, if you're looking at a cyclic reactor, that is more robust. Why? Because the biological process starts after the reactor is full. So what this means is that you have equilibrated the contents of the reactor, whereas a CSTR, continuous flow, is always dynamic. You have something coming in, and if your dilution cannot take care of that variation, then the microbes in there will see that variation very quickly.
Okay, yeah, thank you very much. It's quite interesting. And we have another question saying that that is regarding the sludge. What would be the reason for high sludge volume index in aerobic digestion?
I think I need to clarify here. There is aerobic process as in wastewater treatment, and then there is aerobic digestion as in sludge treatment. All right. In both of these cases, the reason why you could have a high sludge volume index, I assume that the person is asking about SVI, the sludge volume index. Now, the reason why you can have a high sludge volume index is because the morphology, if not the species, at least the morphology of the microbes inside of your population has changed. So typically what this means is that if you put your sample under the microscope, you will begin to see more filaments. Now, why would a population change its morphology, meaning its shape, all right? Why would the population change its shape? One of the key reasons is starvation. So when a population is faced with substrate limitation, then the microbes changes in shape so that it can better search out the next source of food. So filaments allow the microbes to reach out for this food. So as a consequence of substrate limitation, it could be we have gone into endogenous respiration. It could be that you have nutrient limitations, let's say not enough NP, then you could have such filamentous growth multiplying very quickly, and your SVI would then increase substantially.
Yeah, that's fine. Another question with regard to your slides on this pig farms, the wastewater treatment in a larger pig farm. So the question is, what treatment methods are you practiced to treat the digestate? Because the management of the digestate from the pig farm is really a critical, difficult part. So, what type of treatments you are practicing in that?
Okay, you are referring to digesters. So typically what happens then, can you hear me? Can you hear me?
We can hear you, we can hear.
Okay, fine, because my internet connection is, not stable, which was what I was worried about. But fortunately, when I was giving the talk, it was very stable. Right now, the digestate from the anaerobic digesters would go through dewatering. All right, so we would take out the water. The water can then go back to the front of the treatment plant for further treatment, whereas the solids would then be applied as a soil conditioner in an agricultural sense.
Yeah, that's fine. Yeah. So still we are waiting for Professor Wei to join. So
Okay.
he had some internet connection. So if Professor Ning is not tired, it's okay. We can have a very good discussion.
No, I'm fine. Let's continue the discussion until
sure.
Professor Wei can come online.
And then there is another question saying asking that what are the possible approaches to reduce the inhibitory compounds in bioreactors? So one way that already you have answered, that we have to look at the process itself, where that comes. Is there anything created within the system itself and then it's triggered to the inhibition?
Well, the best way, of course, is to try to stop it at the factory.
Yeah.
All right. So if the factory needs to use disinfectants, then it should choose a disinfectant that does not have so long a lasting effect that it will travel on into the treatment plant. Now, the next thing would be dilution. You cannot add in water from the tap to dilute. That is cheating, all right? So what we would need to do is to build holding tanks for the wash water, because factories do not wash all the time. They need to be in production. So this thing only happens when they are washing. So the wash water is then diverted and collected in a separate tank, and we would then bleed this into the main plant. Now, when it's bled into the main plant, the next thing that you would need would be an EQ tank. So this then dilutes the inhibitory material, and it then goes into the biological process. In the biological process itself, the best defense would be microbial population. You want the largest possible microbial population in your reactor, so that even if some of the microbes get killed, you still have enough left to continue the job. All right, so that's how it's done.
Yeah, it's interesting.
Yeah, in the extreme case, what we would do is, let's say, we know that something bad is coming in. We know that our population is not big enough to take the shock. Then what is going to happen is we are going to inject a sorbent into the reactor. Right? Of course, this assumes that your reactor has been designed to take this kind of addition. Otherwise, you create another set of problems. So the idea is that we inject the sorbent into the reactor, almost like we are using an antidote for poisoning.
Okay, yeah, that's fine. So you were in a presentation also, you said that if the populations are in a problematic situation, you can supplement with the enzymes.
Yes.
So you just mean by microbes means enzymes for the hydrological.
Right. We can actually supplement two things. One is we supplement enzymes. Right? Yeah. And this is a situation where we don't have, how would I say it? We don't have spare microbes in the store. If we have spare microbes in the store, then the preference is to supplement microbes.
Okay. Okay. Yeah, that's fine. Yeah, good. So there is another question saying that the inhibitions coming from the substance such as maybe the long chain fatty acid. So you have any experiences with the substances and how you overcome those inhibitors in your experience?
Well, if you're talking about long chain fatty acids, then it may be that the person was referring to anaerobic systems, because if your anaerobic system is not in balance, you then end up with C3, C4, C5 acids. Still not very long, but long enough to cause trouble, right? Now the other possibility is, and this would come if you are dealing with vegetable oils. If you are dealing with, say, wastewater from an oil mill or an oil refinery, then you can have very long chain fatty acids. So you could be having ristic, lauric, stearic, and so on. Now, these are very long chain, definitely more than your C3, C4, C5. And these are also inhibitory. Now, the solution always is to control pH and to control usage. If you lose control of the pH, let's say the pH drops or your concentration spikes, then chances are you will lose your biological process.
Okay, yeah. So yeah, coming back to my questions. So you were telling me that, telling us that after this enhancement of this process integrity, using the sensor system, you can control the system by AI, artificial intelligence. And also you told us that we should not rely completely on AI system, but we have to use the common sense on the systems and experiences. So it was quite interesting. Could you please give us some practical things that tell us, that explain this concept that you want to enhance the integrity, and then you have a sensors, and the sensors give some signals. So we are trying to control by artificial intelligence, but we are not going to rely on that one. But we have to be intelligent than the sensors. So yeah, it's quite interesting here.
Right. Now, typically what happens is we have the sensor systems installed, and the sensors will then be sending signals to the computers, and the computers will be running algorithms, and the AI will then generate, I would say, generate propose action. Now, why is this so? Why is this? So, let me give you an example. So supposing now a wastewater stream is coming in, and the sensors, let's say our electrochemical biological sensor picks up a signal that says, no good, the wastewater contains something very inhibitory, all right? Now, if this signal goes to the AI system, the algorithms will churn, and out comes the proposed action. Cut off the wastewater, right? So the valves, if you leave it to the AI system, the intake valves will close. The intake pumps will shut down. So meaning that the wastewater treatment plant is completely protected from this wastewater. It cannot get into the treatment plant. But if you think about it, if the factory is still running its operation, then if you shut down the intake valves like this, where's the wastewater going to go? All right, the wastewater is spilling all over the place. So this is where human decision will have to come in. You have to weigh out the risk. Which is worse, killing the plant or having wastewater all over the place and then having the government inspectors coming in and making life really tough for you. If you allow the wastewater to come in to the treatment plant, then maybe, like I said earlier on, yes, your biological process may be affected, but I can apply an antidote and try to save the biological process. Minimally, I'm buying time, right? So these are the kind of decisions that the operator in the operations room, looking at all the computer screens, will have to make the decision. Oh, Professor Mowjood, I've lost you. I can't hear you. You are.
Yeah. So yeah, we understood that the AI can propose the solution, but we have to make sure what should be done. Good example that the wastewater is still everywhere because of this AI. So we can't blame the AI, but we have to blame ourselves to be.
Correct. Yes.
Yeah. So participants are typing questions, more questions. So we are selecting only few questions to you. We don't want to make you tired of this. Still, we are waiting for the way to be connected. We could hear some technical problem in connecting. So the next one, so you take little time. Don't worry. It's okay. So what do you think about the biogas collection plant from Kentin? It's a very small question whether this will be effective. From a Kentin, is it possible to have a biogas collection plant?
For what?
The small food restaurant.
Professor Mowjood, I lost you for a while. Could you repeat your question?
Yeah, it is. The question is just, is it possible to have a biogas plant from a small canteen, a cafeteria, or a restaurant with that wastewater and the waste coming from the canteen? So simply, whether it is feasible to have a biogas plant for a canteen.
Well, first of all, technically, I would say yes, it is possible to put in a biogas reactor to deal with canteen food waste. All right, so I must emphasize, it is canteen food waste.
Yeah.
And the food waste has to be carefully sorted. So, for example, you can't have things like a metal spoon. You can't have plastic bags. So it has to be carefully sorted. Now, the most important question, however, is because if there is insufficient waste, then you will not be able to produce enough gas to feed to the burners in the canteen.
Yeah, got it. Yeah, got it. Yeah. So I will have the last questions, Prasanam. So the question is, if a food factory suddenly change the product line, what are the precautions that we should take in order to get the wastewater treatment plant stable if the product line suddenly change?
Well, this is where, if it is something like a food waste, then stability can be reachieved within a fairly short period of time. So we don't.
Yes. Now I'm changing. Yeah, now I'm changing. Okay.
If it's chemical wastewater, then we have to be more careful. And that is why on one of my slides, you will notice that I spoke about identifying the microbes, cultivating, and then harvesting the microbes. So when there is an upset, we actually draw microbes from the store and dose this back into the reactor.
Yeah, so now Professor Wei is connected, and thank you very much, Professor Ning. It's really very pleasant and pleased to answer the question. Yes, Professor Wei, so we are inviting you to take your talk. The title is The Shortcut Process of Combining Magnetic Coagulation.
Wait a minute, sir. So I will change the because
So you can share your screen and then start presentation.
yes, this is my presentation. Yes. So and wait a minute. So and okay. So good evening, everybody. So thank you very much. Thank Professor Muji and thank Professor Shami. And thank you all. So it's great. So I will make a short presentation and about the research. Listen to research. Yes, yes. So and the title is shortcut process combining magnetic coagulation sequence and membrane bioreactor for treating high strength wastewater. This is for swine wastewater and food waste digesting. So and please next. Yeah, I will. Yeah, please next. Yeah. Yeah, I will introduce according to this the part. Yeah, next. Thanks. Yeah, please. I'm sorry. Yeah. EM. So as we know, so there is lots of high strength wastewater, like the swine wastewater, like the just Professor mentioned the peak farmer. So this is also a big problem. The swine wastewater is it's a big threat to our the country in China. So and also that also for the landfill leachate, and wait a minute, I will copy to the computer. So I will share. So yes, and Professor Mochi, can you stop? You are the share the screen. I can do. Yes, this one. Yeah, great. Yeah. So for that, yeah, okay. So as we know, there are lots of kinds of high strength wastewater, like the swine wastewater, the dead industrial wastewater, and anaerobic digest wastewater, something like that. So how to do this? So in China, this is high strength wastewater is a big challenge for us. So for example, for this is a high strength for this one. So for example, so you can see this is the COD and total nitrogen and ammonia nitrogen, and it's very high. So my Sri Lanka student Talentu helped me to find the definition from National Science Foundation of Sri Lanka. So this is for this one. So you can see this, and from this is the typical wastewater for this swine wastewater and food waste digestion. So you can see there is the COD is very high. It's roughly so more than 10,000, and the total nitrogen is also more than 1,000. So that will be ammonia nitrogen is also very high. Generally, they often treated by the anaerobic digestion, and then aerobic treatment, and then something like that is long. The process, like for example, for this one of community use, the community treatment process, this is long process. So it's also a large footprint for the land area. They also use membrane separation, but you know, for the membrane SMBR technology, it will the membrane falling is a big problem. So how to deal with the membrane falling? So because in this high exchange wastewater, the suspended solids is a big concentration. This is a big challenge for this membrane falling control. So there also use some other technologies, membrane separation process, uses the artificiation, nanofiltration, and the RO. But for this technology, is a high cost. Due to this is a high high strain. The membrane falling is also a big issue. Okay, so that is for this is a challenge. Treating this such high strain wastewater in China. For example, there is the cost. This is the area and the efficiency. So we want to small footprint and small area and also high efficiency. So how to do that? So we want to do something like that. As we know, and generally for the high suspended solids wastewater, generally they use the coagulation. But for this one, we want to change. We want a new one, magnetic coagulation, because for this magnetic coagulation, it has very excellent solid liquid separation and can speed the settling and also can reduce the footprint. And also, you mean for the biological nitrogen removal, there are lots of kind of technology like the liquefaction, denitrification for the full process, and but also there for the nitritation and the denitritation, and also for the animals for this. But generally, they will often use this SBR secretion bioreactor. But for this SBR for treatment, for the high strain wastewater treatment, their settling time is very long. So how to deal with this? So we are wondering, so it's possible for us to add the membrane to instead to replace the settling. So that's my idea. But also, you know, for the high strain wastewater, there are also lots of high COD and high ammonia nitrogen, and how to control the very precise about the nitritation and the denitritation. That is very important because, you know, for this process, the control strategy is very important. So that's we want to do something like that. That is for this is for the magnetic coagulation. So this is our proposed process. This is the magnetic coagulation. Then this SMBR is a sequential membrane bioreactor. So this is a shortcut for to treat this is high strength wastewater. We select two kinds of wastewater. One is the swamp wastewater. Other is the food waste digested. So that is we want to do that. So and so this just slide show you the conventional coagulation and magnetic coagulation. So generally, because of magnetic coagulation, they can speed the settling and also remove the excess and total phosphorus quickly. And the block size is also very huge. And for this is for the short biological nitrogen removal. As we know, for example, for the different carbon and nitrogen ratio. So generally, for the carbon nitrogen ratio is 8 to 10, we can use nitrification and dilution because this moment the carbon source is enough. But for the medium carbon and nitrogen ratio is roughly 5 or 6, 5 to 6. This is the carbon source maybe is not enough. So how to deal with this? So we use nitritation and denitritation. So that is ammonia to nitrite. nitride, and then go through here. This is a shortcut, the biological nitrogen removal. But for the low carbon and the nitrogen ratio, it's roughly 1 to 2, even less than 1. So what is the data we can use? This is the NMOX, the ammonia nitrogen, and nitride, and then together to action. So that's the 3 kind of the biological nitrogen removal process. So for this kind of high strength, we use this is the nitritation and denaturation. This is our idea. So, but you know, for this nitritation denaturation, the control is very important. So how to do that? So we want to develop such kind of cost-effective SMBR. So the conventional SBR plus the submembrane, then and also it is also controlled by this real-time control strategy. So this control strategy based on the combined the pH and the ORP feedback. So that is the idea. So and for in our experiment, so we the first magnetic coagulation is as a pre-treatment. For this pre-treatment, so we need to optimize the dosage and the operation parameters. For this is a pre-treatment process. We focus on the suspended solids removal and some turbid removal and also some COD. So that's this. So this is our operation parameters. And this for our SMBR setup in our laboratory is roughly. So we do this experiment more than 250 days. So in the stage 1, we use this SMBR to treat the swine wastewater. In the stage 2, we use this technology to treat the food waste digested. We can see this table. So that's the COD. It's very high. The suspended solid is also very high. Especially you can see this is ammonia and nitrogen. So due to this is ammonia nitrogen in the pH over the 7, there will be free ammonia. The free ammonia will be toxic to the biomass. And we also see the electrolytic conductivity. We can see for the food waste digested, this is very high because there are food waste. There are some salts in the food. So, and we just compare the performance use this combined technology. So, and so we can see, and this is the swine wastewater. This is the food waste digested. So from here, so this is we use magnetic coagulation. There are some the PAC and PM and and this is operation. This is operation to optimize the dosage for PAC, PM, and magnetic seeds. But this one you should mention. This magnetic seeds can be recovered, but in the laboratory, so we don't recover. But in practice, we can recover. This is magnetic seeds. So and from this, the test from you can see this is the performance very good, especially for removing suspended solids and turbidity. And so total phosphorus, we can see all of this is very high, but also for the COD and some can be removed, roughly 30% or 40% can be removed. But for the ammonia, generally it's not removed less. So this magnetic coagulation is very effective to remove some. So this is very good. For this, it will be very good for the subsequent SMBR treatment. For this is the SMBR, so you can see, and both can treat very well. So this is the effluent COD. So effluent COD generally in our country there are different the discharge standards for the sewer system. Generally, there's roughly 500 milligrams per liter. Okay, so this you can see. This is for the generally here's why most of them can be meet. This is the discharge standard, and also this is the move rate is very high. So for the total nitrogen is also very good. You can see this is a total nitrogen can be removed rate both in both the removal rates are both high, more than 95%. So you can see this one. So that is very good for this one. So and and we also so why they can do this? So because we are the stable nitrogen is happening. It happened. So for this technology, nitrate accumulation is very important. If this is not enough, so they will be not good for this nitrogen remove. So for this technology, we don't add the external carbon source. So this we also test the LB activity, and we also need the NOB. So we also can compare or something like that. And also, so this is a different cycle. So as we mentioned, in this is the technology, SBR technology, we are sequencing. Each cycle they are different. So in this cycle, so you can see this feeding and anoxic and oscic and discharging. So you can see all of this is very good because this is real-time control strategy is very effective. It can control very well. So that is very important. And this is also this is real-time control point, just like the value point. When this one the ORP is dropped down, this one it means this is black point. So and we need the start to aeration. So okay, aeration. And then when this is for this is the pH, you see during the aeration, the nitrogen is happened. The pH will drop. So when this drop, then it happens, and then we stop. Then so you use this the pH and RP feedback. You can control the feeding, the wastewater at the carbon source, and also we can control the aeration, the start and stop. So that is our technology. So and this is to show you this is a combined technology, because for this technology it's very short, only 2 units. One is unit mechanical coagulation, and one is SMBR. So you can see this will be very shorter than the conventional process. You can see this is all of this is very high. So for the swine wastewater food-based digestive. So all of this is the suspended solid is not totally removed because the membrane cut off. And also the COD, the nitrogen, the nitrogen, then phosphorus, and also can meet the sure system discharge standards. So because for the different kind of industrial wastewater, China has different discharge standards they can meet for this, but for this one, they still cannot direct discharge into the environment. They also they can do the next municipal wastewater treatment plants. So there also we do some investigations in the microbial community. For the you can see there is most of in both stage. There are some the bacteria is like bacteria, and also the LB is the Nigersomas and the Nigerspira is Nigersomas we can find, but the Nigerspira is very low. Nigerbacter is also very low. And for the dignified function bacteria, this is the same kind. So I don't tell you the details. So anyway, I will make it short conclusions. So this shortcut process, we think is very cost effective, and there also came the performance is excellent for COD and the nitrogen and phosphorus remove and suspension remove. So you can see, and also the mechanical coagulation is a cost-effective pre-treatment method and very cost-effective. And for this, the SMBR, so it's also is very good. So on one reactor and the shortcut. So that's this. So and I think for this is our research. This is innovation. Is that this is combined together. Okay. So and reduce the process because you know for the long treatment process it will acquire a large land area and make the operation and maintenance difficult. For this one, it's very short. So we also want to do the pilot scale in the future. And that is encouragement for this work is carried out by my Sri Lanka student, Talindo. And Tiani and Zhenjiaxi, this work is done by the Talindo. So I thank his great efforts for this work and this something. And thank you all. Thanks. I'm sorry. So for this some connecting problem. Yeah. Thank you.
Thank you very much, Professor Wei, for your very insightful, very interesting presentation. And yeah, we got your point. You have emphasized this magnetic seed coagulation, shortcut biological nitrogen removal, and also the real-time control strategy. So there's three things we feel that it's a very good innovation in the wastewater treatment technology. I think we got the point. So we have one or two questions since the time is limiting. One question is to Professor Wei, can we use that magnetic? Can we reuse that magnetic for this magnetic seed coagulation? And what is the cost compared to the LM, the PAC?
Yes, good question. Generally, conventional coagulations generally use the PAC and the PIM. And for this mechanical coagulation, we still use this one. But we add the magnetic seeds. So this magnetic seeds is just an iron. So, but for this iron, so we can recover it. We can in practice in the engineering, so we can practice, so we can recover. So it's roughly generally the recovery rate is more than 98%. So in practice, for example, in
thank you very much, Professor Wei, for that response. And we have one common questions for both Professor Nink and Professor Wei. How to reduce the inhibitions of sulfur or ammonia in the wastewater treatment system, because we have a problem with this problem in the rubber wastewater treatment, in the rubber industry. Do you think it is an inhibition for sulfur in the ammonia? Because the Professor Wei also said we can get a shortcut for nitrogen removal. So what is your, can I ask Professor Ning first and then move to Professor Wei?
Yes. Professor Mowjood, you mean for the rubber wastewater? For the rubber wastewater?
Rubber wastewater, yeah.
Yes, because I know for the rubber wastewater, there is sulfide is very high.
Yeah.
So for this wastewater, we can try this technology to treat this rubber wastewater. So, but till now we don't have the experience. I already arranged my Sri Lanka PhD student to do some work, because for the high concentration sulfide, so we want to know there is any impact on the treatment process. So for this one, we will do some research. But here now, this moment I don't have no idea about that.
Okay. Yeah. Thank you very much, Professor Nong. Would you like to share your comments?
Yeah, typically, if we are faced with a wastewater with high ammonia, the pre-treatment is to do stripping first. So we would strip the ammonia before we allow the wastewater to enter the bioplant. So that's one way. There are other ways, but that is one common way that we would use. Now, sulfate is a different problem. Sulfate has a problem with anoxic conditions. So when you have sulfate entering an anaerobic reactor, then the pathways are switched away from the regular anaerobic process towards reduction of sulfate. And that is not the only problem. So on the one hand, you have this switch, and you then end up with a lot of the organics not getting degraded. On the other hand, because of this switch, you then end up with the sulfate now being reduced, and you get perhaps sulfur deposits or sulfides. Now, if you have sulfides, then your reactor could undergo a lot of corrosion problems. So we would be very, very careful if we see a lot of sulfate coming through to the treatment plant.
Yeah. Okay. Yeah. Thank you very much, Professor Ning and Professor Wei, for your real valuable contribution to this webinar. And if we have any final message to the participants, you can make. May I ask Professor Wei to give a final message to the participant on this wastewater treatment webinar? You have anything to say? Final message to us, Professor Wei?
Yeah. For this webinar conference, I think it's very good. And but you know, for the industrial wastewater, maybe it's also a big challenge for Sri Lanka in the future, because your country is growing up in the future. So industry maybe it's very important for your country's growth. So, and I think for this moment, so we can work together, or for some high strength industrial wastewater treatment. So then we can try different technology and develop different technology suitable for Sri Lanka, because Sri Lanka is a tropical island country. So the climate change, the temperature, maybe it's suitable for you to use the anaerobic digestion. And the anaerobic digestion, maybe it's very can be used in tropical area, because use this technology we can recover the energy, and also some also can be used as the pre-treatment.
Yeah.
The following, we can use other develop new technology like for this food waste digestive, because you know for the food waste it was a very high exchange. So, but after another digestion, they can cover the energy, but still lots of problem. For this, they use the conventional process. It's very difficult to do that. So we use this one. So that is good. That is interesting.
Thank you very much, Professor Wei, and we are looking forward to have a collaborative work with you in future. So this is a very good interaction with us. Professor Ning, you would like to say some final words with us?
Sure. I must echo what Professor Wei has just said about the Sri Lanka development and the need for industrial wastewater treatment technologies. And certainly the anaerobic process would be one of the technologies that Sri Lanka can consider, because it would allow biogas recovery, and of course that would mean energy recovery. And if you take it further, then you would end up with water recovery. I think the days where we can just treat wastewater and throw it away is very wasteful. So we should look into water reclamation. But I would also want to take the argument another step further. And that is, if you look at the economics of the situation, really biogas and water are not very high value commodities. So even if we recover a lot of biogas and a lot of water, it does not improve the economics of wastewater treatment substantially. In other words, I'm arguing that in fact, wastewater treatment need not be seen as wastewater treatment. Wastewater treatment should be seen as a process where we mine useful materials. And some of these useful materials can be nutrients. We could be looking at nitrogen and phosphorus. For example, we are already mining hormones from food waste so that we can apply it in agriculture. If we are looking at anaerobic digestion, we are now considering the possibility of stopping the process before methanogenesis. So when we get to acidogenesis, that's it. We want to stop it so that we can recover the acids and use the acids for something else. Now, all these were not possible before, but now it's becoming possible because, number one, we have new membranes coming into the market, and number two, the membranes are getting cheap. So this allows us to use the membranes in this manner. And I would like to end by saying thank you very much. It has been a real pleasure involving myself with this webinar. And of course, it has been a pleasure to meet up with Professor Wei as well. It's good to see a face, a person that I've been looking at for quite a while. And I would also like to say thank you and my good wishes to all friends and colleagues in Sri Lanka.
Thank you very much, Professor Nink. The way you advise us to look at the wastewater treatment plant as a mining place for our material to recover and reuse it. So it's a very good message that all of us can get into think. So we are, on behalf of the organizers, we are thanking Professor Nink and Professor Wei for your time and the dedication, the commitment to make this webinar successful. And then we had a very good idea. And the student point of view, they may have some more questions. So they will, we have shared your email address to them. So they may get, you may get some questions. So hopefully you will help them to solve their problems. So once again, I personally thank Professor Nink and Professor Wei. And I'm also very happy that both of you have now seen each other, and then you can continue your collaboration, because we see the synergy of this group presentation. Although the time has gone, you were here with us always, and that was really an encouragement for all of us. I also take this opportunity to thank all the participants for their active participation in this program. So I wish you all the best, and we will meet you again the third webinar that is on environmental impact assessment on 15th at the same time. And the last seminar is on water quality monitoring, that is on 16th at the same time. So we look forward all of you to join these webinars and then contribution. Thank you very much. Wish you all the best.
Thank you. Bye.
Thank you. Thank you, Professor.
Thank you. Thank you. Bye bye. Bye.